Hello students, I hope everybody is doing great and amazing. I'm here again with another magnificent question series from the topic General Organic Chemistry. So let's start students. We have the first question. A compound beta-naphtol has been given to you which has been reacted with NaOH and further is asking you to calculate the number of secondary carbanion structures. So first let us understand the reaction here. This OH group is an acidic. You have a base. The OH minus picks up the H plus ion. Once it picks up the H plus ion, this H plus and OH minus will form the water and it forms the corresponding beta naphthoxide. Actually, students, this is very much similar to a PYQ in JEE Advanced, where he has asked you to calculate the number of resonating structures. The reason why I have picked up this question is many students do make mistake in calculating the number of resonating structures, especially with the benzene ring containing compounds. So I'll give you a very simple trick as well as a concept so that you can easily decode this, how to calculate the number of resonating structures without having any ambiguity. Let's see. This itself is one of the resonating structure, guys. So this type of system where the benzene ring electrons, the pi electrons of the benzene ring has been arranged in this format. Okay. So let me take the other resonating structure. You can have in another format, in another form, where I will fix the position of the double bonds of the second ring and I will change the position of the double bonds in the first ring. So you will have something like this. So this is the second resonating structure. I hope everybody has followed. Now you can have one more where you can fix the position of the double bonds in the first and the second double bond in the first ring and make a benzene ring in the other ring. So this is the third resonating structure. So in total, you have 3 resonating structures so far with reference to the benzene ring, right? Now we can proceed further. How do we proceed further? You can pick up any one of the resonating structure and you can follow the resonance. So I will take the first part where there is an lone pair pi conjugation. So you will have a negative charge here and double bond O. The other pi bonds will remain as it is. Next, we'll move further. Again, you have negative pi conjugation. So the pi bond has to be shifted so that a positive charge will be generated and negative and positive charge will form another pi bond. So here you have a negative charge. So this pi bond, you have a double bond O, and the other 2 pi bonds will remain as it is. Here, the negative charge is a kind of cross conjugation where it can move to this end on the right hand side and even as the left hand side. So let us make one of them. So if this negative charge is delocalized in this direction, so we have to shift the bond in this direction. So what will be the other resonating structure? You will have a pi bond here, you will get a negative charge and a double bond O. Then other pi bonds will remain as it is. Is it clear? We will not draw the other resonating structure in continuation to this, because if the negative charge now will go from carbon to oxygen, where already with oxygen having possible negative charges, resonating structures are already done, right? Now we will take up this and move further. So you have a negative charge here. So this negative charge can further delocalize in this direction and you will get another new resonating structure. So here you are going to get a negative charge. So here you will have a pi bond. the already existing pi bonds will remain as it is. Clear? Next, we can have one more resonating structure. You have a negative charge here and a double bond O, and another pi bond. Can this negative charge can further involve in delocalization? Yes, still. You have a negative charge here and double bond O and a pi bond here. So further we will not delocalize. Why? Because again the negative charge on oxygen will be repeated in one of the resonating structure. Now let us calculate how many resonating structures we have. So this is the first one, this is the second one, this is the third one, with reference to where the negative charge is on the oxygen atom. Then this is the fourth one, this is the fifth one, this is the sixth one, this is the seventh one, this is the eighth one, and this is the ninth one. So total how many resonating structures have we seen? Possibly 9. So what is the concept here? Whenever you have this kind of multiple benzene rings with there is an heteroatom where delocalization is possible from the electron pair on the heteroatom to the ring, first you try to draw the possible resonating structures by changing the position of the double bonds of the benzene rings. Once that is done, pick up any one of the resonating structures and then you try to draw the resonating structures. Then there will be no question of repeating or there will be no question of any mistake. But only one point you have to check: when you have a negative charge or a positive charge created in the system, is there is a possible for cross conjugation. If you just look at that, and let me tell you students, there will be no scope of doing any mistake. So let us come to the question now. How many number of secondary carbanions you have? So in these three we don't have any carbanion. So this is one structure where we have the secondary carbanion. That is the fourth one. Here this is tertiary carbanion in the fifth one. So this is another structure 6 where we have the secondary carbanion. In seventh also we have the secondary carbanion. In eighth also we have the secondary carbanion, the fourth one total, and here also we have a secondary carbanion. So total, how many number of secondary carbanions are formed? It is 5. So he may ask you a number of questions based on this. He may ask you number of primary carbanion or tertiary carbanion or secondary carbanion. Or he may ask you how many resonating structures are possible where you can have a negative charge on oxygen atom. Then definitely how many resonating structures you will have? 3. If he is asking total resonating structures, definitely it is 9. Followed? So students, let's move to the second question. Here is asking you to compare the bond length between P, Q and R. If you have closely followed, this is a condition of cross conjugation. What do you mean by cross conjugation? Where you see, if I take this is pi 1, this pi bond as pi 2 and this pi bond as pi 3. Pi 1 and pi 2 are in conjugation. Pi 2 and pi 3 are in conjugation. But pi 1 and pi 3, they are not in conjugation. So this pi 2 is in conjugation simultaneously with both pi 1 and pi 2. This is what we call it as cross conjugation. Right? Fine. So how do you compare the bond length? Normally, students, what do? Usually they try to draw the resonating structures. From the resonating structures, they try to get the answer. Yes, that is the approach. No doubt about it. We have to draw the resonating structures, then only we can see which one is having maximum partial double bond character or maximum single bond character. But beyond that, there is one more concept which you need to apply. If you miss that, then definitely our result will be wrong. So first let me draw the resonating structures and then we can arrive at that conclusion. So if I consider pi 1, pi 2 initially involving in resonance. So you can expect to have the resonating structure something like this. Here you have a negative charge, here you have positive charge. So pi bond will be formed here. So here you will have a positive charge, and here you will have a negative charge. Alternatively, there will be another, as it is the other pi bond. Alternatively, we can have one more possible resonating structure here, where you can shift the pi bond the other way. Then, what is the new resonating structure we will have? Here, where you have positive charge, here you will have a negative charge. Where you have a negative, here you will have a positive charge. But the pi 3 bond will remain as it is. Suppose, if I want to compare the conjugation between pi 2 and pi 3, so that when pi 2 and pi 3 involve in resonance, so as I shifted the pi 2 bond here towards this carbon atom having a negative and here positive, we can have the alternate direction here. So when you are negative and positive, it can form a bond. So what is the other resonating structure you can have? This double bond will remain as it is. Here you will have a new pi bond. This will have a positive charge and this will have a negative charge. The other possible resonating structure, you will have something like this. Here you will have negative charge, here you will have positive charge. The other double bond will remain as it is. Right? So I have drawn the resonating structures, possible resonating structures. One set is for when pi 1, pi 2 are involving in resonance, and other set is when pi 2 and pi 3 are involving in resonance. But if you compare or understand the basic rules to compare the stability of resonating structures, it is always a neutral one will have major contribution. In the conditions of resonance, you would have studied that when you have multiple resonating structures, we should take consideration of the energy. Usually, the energy of the resonating structures or energy of the contributing structures should be less. If the energy difference is very high, then the contribution will be major from the one which is having less energy. Like in this case, the major contribution will be with this resonating structure. And this entire set will be less contribution. When you have major contribution in the resonance hybrid, then you have to compare the bond length first importantly based on this resonating structure. Then you have to compare with the less contributing resonating structure. In this, it's very clear that Q is a single bonded one. Q is a single bonded one. Both P and R are double bonded. So from the major contributing, you have seen that Q is having a greater bond length. Now, how do you compare P and R? So for that, we can follow these resonating structures which have relatively less contribution. So why did I take the first one? Because it is having major contribution for the resonance hybrid. Clear? Now let's see. In these resonating structures, if I take this is 1, this is 2, this is 3, and this is 4. In 1 and 2, where you have the bond length between carbon-carbon for P, it is single bonded. In 3 and 4, it is double bonded. So two resonating structures where P is double bonded, two resonating structures where you have double bonded. Now let us come to R. In all the resonating structures, 1, 2, 3, 4, you see R is singly bonded. R is singly bonded. When it is singly bonded, then after Q, you will have R. Then obviously P. If you don't apply this concept, definitely you will take R as the major contributor and hence it will have the maximum bond length, which is incorrect. All these are charged spaces. Definitely their contribution will be relatively less for the resonance ion. Is that clear, guys? So this is where the students make mistake. Right, students, let's move to the next question. Give the direction of dipole moment. You need to give the direction of dipole moment. Suppose if you take a covalent molecule and it is a polar. Say suppose AB you have, where electronegativity of A is greater than electronegativity of B. In such case, how will you have the direction of dipole, where you will have partial negative charge and here you have a partial positive charge. Where you have a partial negative charge, there you need to put the head of the arrow, and where you have partial positive charge, which is called as the tail of the arrow. This is how you show the direction of dipole. Similarly, in this compound, pyridine, it is a heterocyclic aromatic compound, is asking you to give the direction. So definitely we need to know the partial positive and partial negative. On which atom, on which carbon atom you have partial negative or partial positive, or on the nitrogen atom we need to check. How will you check? Through resonating structures only. So instead of asking you to calculate the number of resonating structures, through the calculation of number of resonating structures, you need to give the direction of the dipole moment. So it is a completely a basic fundamental question, right? So let's solve. So let me draw the resonating structure first. So here you have a lone pair. Will the lone pair involve in resonance? No, because the lone pair is present in the sp2 hybrid orbital. And if you know or you have attended the first session, students, I made it very clear that an atom can give only one orbital to involve in resonance. Already nitrogen atom has given one p orbital to involve in resonance. So definitely it can't give one more orbital to involve in resonance. Is it clear? So let us try to draw the resonating structure. So first the pi bond breaks. Thereby this nitrogen will have a negative charge, and on this carbon you will have positive charge, and the other two pi bonds will remain as it is. So further it can involve in resonance, positive pi conjugation. So you have to shift the pi bond in this direction. So here you will get a pi bond and here you will have a positive charge. Once you get a positive charge here, again positive pi conjugation. So here there is a pi bond again. So here you will have positive charge. And here you have a negative charge. So this positive negative will give you another pi bond. So in total, how many resonating structures you have for pyridine? So this is 1, this is 2, this is 3, this is 4, and this is 5. So in total, you have 5 resonating structures. And if you see on which atoms you have the positive charge. On this carbon atom you have positive charge, and on this carbon atom you have positive charge, and on this carbon atom you have positive charge, and ultimately nitrogen atom is having the negative charge. So the direction of the dipole will be in this direction. Is it? No, it is wrong. It should be opposite, right? Nitrogen is electronegative. So this will be the correct one. Did you understand? I hope you have got the concept, guys. Chalo. It's a very good question, right? Chalo. Let's move to the next one. Yes. The correct stability order of the following resonating structures. Students, I have given you, or I have picked up only those questions where students do make a mistake. It's not that the students are not aware of the concept. Students are not aware of the correct approach. That is the reason I have picked up these questions. If you have seen the previous two sessions and this session, obviously in this session the uniqueness is that I have touched only on those concepts where students do make mistake, right? So let's see the correct stability order of the following resonating structures. You have to check the order, stability order. Whenever you are comparing the stability order of the resonating structures, there is a certain priority order. Based on that priority order only you have to determine. Randomly you cannot pick up a rule and you cannot apply. That is the first mistake where students are not aware of the priority order. Second, the other mistake what they do is that they take these rules and they try to compare different compounds involving in resonance. No, you cannot take these rules and apply for compounds involving in resonance. What I mean to say is that if a particular compound is involving in resonance and if you have 1, 2, 3, 4 resonating structures, these rules are applicable to compare the stability of those resonating structures. You cannot take two compounds involving in resonance and you cannot apply these rules, right? Sure. So first I'll give you the priority order. So the first thing is that you have to check the number of covalent bonds. You have to check the number of covalent bonds or pi bonds. Greater the number of covalent bonds or greater the number of pi bonds, greater will be the stability. What is the second one? The second one is the maximum number of atoms having octet configuration. Maximum number of atoms having octet configuration. Greater the number of atoms having octet configuration, greater will be the stability. This is the second rule which you need to apply. If the first one fails, then you need to go for the second one. But actually if you see, both the rules will complement each other. That means whenever you have maximum number of pi bonds, definitely you will have maximum number of atoms involving or having octet configuration. Third is the neutral resonating structure is always more stable than charged ones. Of course, in the resonating structures, the charges have to be maintained. If you have a neutral resonating structure, in the other resonating structures, you have charges, but they maintain the total charge will remain the same, no doubt about it, right? But the one having neutral resonating structure is more stable. That is the third rule. If this rule is also unable to determine the stability order, then we need to go for the fourth one. What is the fourth one? Negative charge on electronegative atom, positive charge on electropositive atom is highly stable. This is the fourth one. Then you have to apply the fifth one. Positive and negative, when they are close, they are stable. Opposite charges attract each other. Still, if you can't really compare, then you need to apply plus I or minus I. Plus I or minus I. Plus I or minus I is governed by DNP rule. DNP rule. What is DNP rule? Distance, number, priority. Distance, number, priority. Priority is given the least priority here. So directly you can't take priority order, guys. Okay. And last one is based on the benzenoid structures. Greater the number of benzenoid structures, greater will be the stability. So these are the total 7 set of rules which you have to follow in the same order. You cannot cannot miss. So even for solving this question, we will follow this order where we will compare one by one. The first one is asking you to compare the number of pi bonds. In the first one, you have how many pi bonds? 2 pi bonds. In the second one, you have is a triple bond and a single bond. So this is also having 2 pi bonds. Third one is also having 2 pi bonds. But in the fourth one, you have only 1 pi bond. So one thing is very clear, that fourth one is least stable. Is least stable. The correct stability order of the following resonating structures. You need to give the correct stability order. So one thing we have decided, that fourth one is least stable. Now we need to compare between 1, 2 and 3. Now, let me take the second one. Maximum number of atoms having octet configuration. Octet configuration. See, in the first resonating structure, the carbon, both the nitrogens, nitrogen with positive charge will form 4 covalent bonds. So it is already having octet configuration. Here you have a negative charge with 2 lone pairs and you have 2 covalent bonds, so 8 electrons. So all the atoms in the first one are having octet configuration. In the second one, you see, yes, the carbocation, it is not octet. It is 6 electron system. So obviously, if you compare 1 and 2, definitely 2 is less stable. Let us see at the third one. In the third one, the nitrogen atom is having positive charge, 8 electron system. This is also 8 electron system. So from 1, 2 and 3, which one will be less stable? Definitely 6 electron system, 2 will be less stable. So first we have seen fourth, which is least stable, followed by 2. So now we need to compare between 1 and 3. There is now a tug of war between 1 and 3. How do you compare the stability between 1 and 3? We have applied first rule, we have applied second rule. Third one, neutral resonating structures. None of them are neutral ones. They are the charged ones. So this one also failed. So we'll move to the next one. Negative charge on electronegative, positive charge on electropositive. Obviously, I believe we can decode from this. Yes. You see, in the first resonating structure, you have positive charge on nitrogen, negative charge on nitrogen. And in the third one, you have positive charge on nitrogen, negative charge on carbon. Negative charge on nitrogen and negative charge on carbon, out of these two, which one is more stable? Obviously, negative charge on nitrogen is more stable than negative charge on carbon. So out of 1 and 3, definitely my vote will go to, of course your vote guys, will go to the first one. So first one is more stable, followed by third one, followed by second one, followed by fourth one. So I believe guys, this is a very good question, which will help you to revise the entire concept regarding resonance stability rules. Remember what I have mentioned, that these rules are applicable to compare the stability of the resonating structures, not for the compounds involving in resonance. Two different compounds involving resonance, and you cannot apply these rules. Right? Let's move to the next one. There are 3 canonical structures of naphthalene. Examine them and find the correct statement among the following. All carbon-carbon bonds of same length. Can you believe? No. Certain carbon atoms will have partial double bond character. Some will have partial single bond character. So obviously the first statement is incorrect. C1C2 bond is shorter than C2C3. C1C2. C1C2. C1C2 bond is shorter than C2C3. Is it? Let's check. If I take this is the first resonating structure, this is the second one, and this is the third one. In the first one, C1C2 is double bond. In the second one, C1, C2 is single bond. In the third one, C1, C2 is again double bond. So you have double bond, single bond, double bond. So it's very clear that double bond character is more. Let us check with C2, C3. C2, C3. C2, C3 in the first one, it's a single bond. In the second one, it is a single bond, double bond. No, it is double bond. In the third one, again C2, C3 is a single bond. So you have more single bond character. Greater the single bond character, greater will be the bond length. So it's very clear that C2, C3 is greater than C1, C2, or C1, C2 is less than C2, C3. So the second option is C1, C2 bond is shorter than C2, C3, which the statement stands correct. Clear? Suppose if he hasn't really given these resonating structures and he has given only the resonance hybrid, and if you have to compare, then how would you solve? You have to draw all the possible resonating structures and you have to designate the respective carbon atoms, and then you need to solve. I hope this one is also crystal clear. Great. I know my students. I have full faith in my students. They are really learning the concepts well. So please do attend all our sessions regularly, as well as your classroom sessions are also equally important. Always, students, whatever you have the extra input or extra subject, whatever you gain from these YouTube channels, they are secondary. The primary ones is your regular classroom, because most of the time you always spend there only. Once you are very clear with the concepts taught in the class, then you can take all these additional help. Shalom. Let's move to the last question for this session, guys. Yes. Which of the following is the strongest base? I think at least in each series, at least I'm giving one question related into the basic character. Such an important topic it is. Basic character is definitely based on the ability of the nitrogen to donate the electron pair. If the nitrogen containing lone pair is involved in resonance, availability of the lone pair is less, so basic strength will be less. So what we will do? First we will see whether the lone pair is involving in resonance or not. So the lone pair on this nitrogen, this is aniline, is actively involving resonance. So when it is involving resonance, its basic strength will be less. So this is definitely out of race. Second one, this is dimethylamine. This will also involve in resonance, but if you compare, relatively it may be more basic. But as the lone pair is involved in resonance, its basic strength will be less. Now let us have a look at the third one. Here at the para position, students, you have NO2 as well as at ortho positions. NH2 group, will it involve in SIR effect? No, it does not involve in SIR effect. Rather, it involves in SIP effect. What is SIP? Steric inhibition of protonation. Steric inhibition of protonation means ability to accept the H plus ion will be reduced. Why? On accepting the H plus ion, there will be an increased steric repulsions because the groups are at ortho positions. So due to which, when you have SIP effect, basic strength decreases. Let's have a look at the fourth one. Yes, this is dimethylamine. Along with you have ortho para positions having NO2. So do you think that will it Least basic? No, not at all. Aniline can't involve in SIR effect, but aniline derivatives can involve. So dimethyl aniline derivative, I mean dimethyl aniline ortho substituted one can involve in SIR effect. Steric inhibition of resonance. I think in the last session also we had 1 or 2 questions based on SIR effect. Steric inhibition of resonance. Resonance is inhibited. When resonance is inhibited, lone pair is available. When lone pair is available, what happens to its basic strength? Basic strength definitely increases because the lone pair is available. Okay, before going for this conclusion, does it involve in SIP? Yes, it involves in SIP. So with SIP, basic strength should decrease, but SIR dominates over SIP. So definitely the basic strength for this compound will be the maximum out of all the combinations. Right, students, I hope you have enjoyed this session. Let me tell you, this is something unique session where we have seen at most basic fundamental concepts related to resonance where students do make mistakes. So if you have any doubts, as usual, please share your comments in the chat box. Definitely I will reply to it. So wishing you all the best. Signing off. I'll come up with another fantastic session very soon, students. Bye bye. Signing off.